The purpose is to have some more interactive sessions and eventually more research-related works within the framework of our mathematical structures. So let's start with that. No, why is it not working? I have to put it on slideshow mode. Okay. Okay, so as I said, this is not a talk to report on research findings on quantals. Neither this is a lecture on quantals. Of course, I am not an expert on quantals to give a lectures on quantals. Just to share some of the observations that may lead some research discussions or other research topics, basically cross subject. That's the most important thing, because all of us are working in our areas which we love to work, but now maybe time to think that how we can talk with each other more from the scientific point of view. And the idea is to discuss possible new research collaborations on quantals under this framework of our mathematical structure program under NITEX. And hence, obviously, to build new international collaborations with our universities in South Africa, and naturally, as a part of it, also to start some joint supervisions of MSc and PhD students, where the topics will not be on one specific area of research, but cross-disciplinary type of things. So the first question you may, sorry, is there a problem, Zurab?
No, there's no problem.
Oh, okay, so sure, thank you. So first question is, why quantals? I mean, there are many mathematical structures, but why quantals? Because I just for more, over an year, I started to look at this area of quantals, and I found that it's naturally connected with various areas of mathematics, starting from general topology, quantum mechanics, point pre-topology, non-commutative rings, mathematical logic, function analysis. I mean, if you read these topics, and then we can immediately see that we have many experts in many of these areas in South Africa specifically, and that also another appealing thing to me, that we should choose some topic which is suitable for the context in South Africa, or mathematicians in South Africa. And that is why I thought maybe quantal could be one mathematical structure to bring people more closer to each other from the research point of view. Okay, so who invented this quantum? It's not very old in some sense. It's actually Mulvey who came up with this in a conference proceedings. And if we read this Math Science review of his paper, that he wanted to actually create a foundation for the quantum mechanics, which would be a non-commutative version of locals in some sense. And he wanted to also relate it with this non-commutative logic modeled on the lattice of closed left ideals of a non-commutative system algebra. So if you just read this first line of this review of his paper, it immediately shows how nicely this notion possibly can connect quite a wide different areas of mathematics as well as even physics, quantum physics. So it already gives us a smell of connecting logic, function analysis, algebra, and physics as well. So the question is then, what is a quantal? So quantal is just a complete lattice with one extra binary operations on it, which is an associative operation. And this operation actually distributes over arbitrary join on the left and on the right. So this was the original definitions of Mulvey. And then we can, as we know that once we have one mathematical structure, we can impose further conditions to get much richer structure on it. So if our binary operation or the multiplication, what we generally call, if it is commutative, and then or the quantal will be commutative quantal, as well as generally we consider the top element of our lattice as the multiplicative identity, and then we call it unital quantal, just like how we call unital rings when we have multiplicative identity rings. One should also notice, or actually note here, that there is a notion of multiplicative lattice much earlier than this notion of quantals, 1960s, by Dilworth, where he actually defined a mathematical structure which is essentially, in terms of quantal, will be nothing but a commutative unital quantum. And if you actually search on Google, you will find plenty of works actually done on multiplicative lattices long before the discovery of quantals, because quantals was the main purpose of this, capturing the non-commutative view of foundation of the sister algebras things, where they needed to develop the foundation of quantum mechanics. But Dilworth's thing was to understand that how much ring theoretic things can be extracted in a more general setup of a lattice. And that is why he was actually more interested on this commutative ring with identity. And that is why we see his definition eventually becomes a commutative unital quantum. So one can study quantals in the two different levels. One is the general level of a quantal without assuming that our multiplication is commutative, without assuming that it has a multiplicative identity. Otherwise, if somebody wanted to see that how much ring theoretic or similar type of commutative structures can be extracted, then one can actually think more on the multiplicative lattice side. So now let us see some of the connections or the relations how quantals naturally appear in different areas of mathematics. So my interest in quantals just for a year. Before that, let's see some examples, because without examples, it may not motivate us how quantals may appear. So one of the very simplest mathematical structure, what we can think of, is the semigroup as a set with a binary operation. And then if we take set of all subsets, then it's actually a commutative, it's actually a quantal, and then of course we can make it a unital commutative depending we tweak our semigroup into a commutative monoid or not. The other example is naturally comes from the rings. We can think either commutative or non-commutative ring. And then if we take all the ideals with the multiplication of ideals as the product operation of our quantals, then all the set of ideals actually forms a nice quantals. And in a commutative case, it will be a unital commutative quantum. Then very important example is point free topology, and every frame is indeed a quantum. And here our multiplication operation of the quantum actually coincide with our meet operation of the lattice structure. So this is one of the widely used or studied area of quantals in a very specific context, where this extra operation coincides with the operation of this underlying lattice structure. Then one can actually think of some examples from the logic, from the formal language. And finally, also, one can see there is a natural example of a quantal in function analysis, that if we consider the lattice of closed right ideals, because generally in sister algebras or in function analysis, we do not assume the commutativity even on Banach algebras. And that was one of the reasons that why Mulvey started on this non-commutative version. So if we consider these closed right ideals of sister algebra, that also gives an example of quantals. So just from this example, we can immediately see that quantal appears in algebra, quantal appears in point free topology, it appears in logic, it appears in function analysis. So since my introductions is with quantal started with connection with rings, and that's so far what I have did some work on the rings. So let me start with rings, and I hope some point of time I will also explore the connections of quantals with other areas. So what is happening in rings if we consider with multiplicative lattices? Because I was working on mainly with the commutative rings with one, and then the corresponding quantal version will be naturally commutative unital quantals, which is nothing but the multiplicative lattice in a Dilworth sense. So we can actually copy literally many of the results of ring theory to multiplicative lattices. For example, if you see this first thing, the product of two ideals is a subset of their intersection, which is absolutely natural exercise. And with little bit of calculations, one can actually prove the similar things with respect to elements also holds for multiplicative lattice. And apparently this inequality is very, very important when we study rings, especially commutative rings, both algebraically as well as when you study ideals topologically, especially the Zariski topology and algebraic geometry, because it gives so-called the Kuratowski closure operator on our underlying set of prime ideals. And see, without this, we cannot have actually a closure operator, and we cannot have this Zariski topology as we find it. So we immediately see we can have already some nice properties which can be copied from rings to multiplicative lattices. One of the most important class of ideals in rings is nothing but prime ideals. And as we know, the prime ideal means if the product is there, then one of them is there. Exactly the same way we can actually copy with terms of elements, that if the product of two elements is below of an element, then one of them will be below. So one can literally translate these definitions of various classes of ideals to the corresponding elements in the multiplicative lattices. The next one is something which may not you have seen. This is another class of ideal, and it is called strongly irreducible ideal. That if the intersection of two ideals is contained in another ideal, then one of them is containing in another ideal. This is a very strong condition, because why suddenly if the small portion is contained, the original ones, one of them will be contained. And exactly the same way, we can actually copy on the right hand side by elements. Now, if we not working on multiplicative lattice, if we are working on frames or say in a general lattice, then we can see there is no difference between prime ideals or prime elements and meet irreducible elements, because there is no notion of multiplications in frames or in general lattice. So multiplicative lattices actually allow us to distinguish between prime elements and meet irreducible elements, just like as we have the corresponding things in the case of rings, because prime ideals and strongly irreducible ideals are quite different things. And why we care about strongly irreducible ideals, because it turns out that whenever we wanted to impose and Hall-Kernel topology, then the largest class of ideals on which we can endow a Hall-Kernel topology is nothing but strongly irreducible ideals. And one can easily show that every prime ideal is actually a strongly reducible ideal. So we have this chain of subclasses of strongly reducible ideals, namely maximal ideals. Is every maximal ideal is a prime ideal, every prime ideal is a strongly reducible ideal. So strongly reducible ideals plays plays a very crucial role from the topological point of view, because it allows us the maximum level of class for the ideals for which we can actually end up Hall-Kernel topology. So similar things we can do in multiplicative lattices, but not necessarily in frames, because we will not see the difference between two. And one very important notion is the radical of an ideal, and exactly the definition is a copy of the corresponding definition for the ring case. And then in multiplicative lattice, or in general for any, even in frames of lattices, there is something called compact elements, which copies the notion of compactness in a topological case. It's the finite cover type of things. I do not know any corresponding type of ideals which represents these compact elements for lattices or multiplicative lattices. Maybe it is widely known, but it is not known to me. Then something which is very, very important is that if we take all prime ideals of a ring, and if we endow a Zariski topology on it, it's actually a spectral space. So what is a spectral space? It's a quasi-compact, which is mean compact, sober. It has a base with quasi-compact open subspaces, which is closed under finite intersections. Now, if we take a definition of multiplicative lattice, what I mentioned, not that one, but what it is written here in the bottom, according to this paper, then it turns out that we cannot just copy everything from ring and expecting that everything to hold for these multiplicative lattices. And in this paper, by Facchini, Finocchiaro, Janel actually proved gives some sufficient conditions for spec L, where L is a multiplicative lattice in the sense that it is just a complete lattice satisfying this first property what he wrote in this table. So if we consider that as a definition, then actually spec L is not in general spectral space. It requires some other properties. So the point is that many classes of ideals have been studied in rings, especially for commutative rings and also non-commutative rings like primitive ideals, which do not appear in the context of commutative rings because it coincides with maximal ring. So it's all of them, almost all of them can be literally translated in the corresponding element form in multiplicative lattices, and one can then see how the properties looks like when you actually translate from the rings to the lattice structures. Similarly, many topologies have been studied on these various classes of ideals. So the same question can be asked that how they look like topological spaces when you consider the corresponding types of elements on the multiplicative lattices. And this literally is a huge research area. And even almost on a daily basis, people coming up with papers on multiplicative lattices, generalizing or extending, in some sense, the results of the commutative rings. Another interesting thing possibly could be studying the subspaces of the spec L from the point of view, because we can, as I just mentioned, that maximal elements will be a set of maximal elements with the Zariski topology will be a subspace, set of prime elements will be a subspace. And to best of my knowledge, and after talking with Finocchiaro, who is actually expert on this commutative algebra as well as on ring theory, spectral spaces more specifically, he said that not much is actually known to study these various subspaces of a spec L in a general order multiplicative lattices. Even the same is not known for the ring, but spec L will be much more scarce to find. Then another interesting thing could be possible extensions of this idea of commutative algebra of rings to the commutative algebra of quantals. So basically, we already know there is a notion of modules over, abelian group structure as the sublattice and the definition of a module. So the question is the results of commutative algebra to do the same thing over quantals, replacing the ring with this multiplicative lattices in general instead of quantals. This itself is a huge, I mean, to me, this could be a wide opportunity to explore that, because commutative algebra is in the scenario since 1940s, 50s, one of the basic reasons to develop that tool specifically for algebraic geometry. And the question is that what about doing, maybe it's too ambitious, but nevertheless, let me say that doing some kind of algebraic geometry over quantals, and there are already notions of sheaves and pre-sheaves of quantals, and there are papers by Borso and others who actually develop these things. So there could be immense possibilities to use quantals as a starting point and redo these kind of things which have been done for last, say, 80, 90 years. Okay, maybe too much about rings. Now let's see topology. We know there are thousands of topologies have been studied for the last 200 years or so. So the question is, if we actually take some of these very well-known topologies and redo the things with respect to quantals, how the things will appear. Because many of these topologies, for example, a couple of years I had a master student, Michaela Hunsler. Her master thesis was to study all these topologies for even for only for prime spectrum of a ring, commutative ring with one. And it turns out that some of the topologies will coincide with each other, and many of the topological properties or spec R with respect to these topologies are actually not being studied. So the question is, if we do the same thing for spec L, and do this kind of study, that could be quite different, because as you see that one may not be able to copy even the results from rings to multiplicative lattices. So this could be one possibility to see how far we can actually extend these things. The other thing is that metric spaces, we know that metric spaces, the codomain of the function is nothing but the positive real, including 0. And then in this paper of Flagg, I do not know how to pronounce Flagg or Flagg, there are two G's. Anyway, so he actually tried to understand that what specific properties of this part of the reals we are actually using to study these metric spaces. And here are a few extractions from his paper that what he's saying that these kind of structures we are using. And basically in this paper, he initiated, maybe he was not the first person, maybe there could be other people who also thought about this and wrote this, but I found this paper is quite elaborately discussed or brought this issue that what about doing metric spaces over quantals instead of reals? And there are some works done along these extensions of metric spaces over quantals rather than reals, but not much. And on the other side, as you know, that metric spaces is a huge research areas, I mean, for various reasons. And it has also these geometric aspects of the metric spaces, which extends up to this differential geometry level. So there could be some many new interesting results one can come up if we actually trying to replace these reals by the quantals. May not be these kind of extractions what Flagg is suggesting, but it could be some other kind of axioms we may consider on this underlying. His consideration is to take a completely distributive quantal where completely distributive in this following sense. But at least it shows that there is an opportunity to use quantals to study metric spaces in a more general form. So this could be interesting. The other one could be studying specifically the connectedness properties, various kinds of connectedness on quantals. So far, to best of my knowledge, I only found one paper, which is also written in Chinese. And of course, I do not know Chinese, I couldn't read, and it's also a very small paper. They apparently studied some of the properties of this connectedness over the quantals. But as we know, from the topological spaces point of view, connectedness is a huge interest for many different reasons. So that could be one of the topological properties one can actually think to study over the quantals instead of underlying set. Okay, so after topology, let's see something on functional analysis. Bourseau and Rossisky with Bose actually wrote a paper on quantals and sister algebras. Remember that Moulvey was trying to use these quantals for the non-commutative version of the sister algebras. And in this paper, specifically, as I mentioned this example, that if we take the closed right ideals of sister algebra, that itself forms a quantal. So we have a natural example of a quantally functionalisis. Moreover, this plays a very characteristic roles to determine the structure of the original sister algebra. And namely, if your sister algebra is commutative, if and only if the corresponding quantal is commutative quantal. And also, if we have a sister algebra homomorphism, then the corresponding lattice structure also becomes a quantal homomorphism. So one can immediately get a smell here. There is some kind of possible functoriality study one can actually think here. That could be also interesting from the categorical perspective. There are a few more results in this paper, which actually associates sister algebras with the quantals in a natural way. And then there is a paper by on these Z ideals and D ideals in the Reed spaces. It's actually 3 papers written with the same title. Only the last one has the second author only. And Z ideals actually been invented, or rather studied first, for the rings of real-valued continuous functions, very widely. And the book by Gilman and Jarrison, Rings of Continuous Functions, became an authoritative source to see these Z ideals for CX. But later on, these Z ideals have been generalized for rings, even for non-commutative rings. And also very recently, it has been generalized as a Z elements for multiplicative lattices. And one of them is actually currently Themba and I looking at some of these aspects on this point of view. But this paper is actually concentrating that
Sorry to
the
interrupt,
several notions
Amorto.
and this.
If I
Sure,
can
sure.
interrupt this, I want to welcome Anke, who joined us only now because she sent us an email and I didn't notice that she wasn't able to get in because of there not being a number or a passcode number she didn't have. So welcome, Anke. And maybe if, Amorto, you could repeat what you said about read spaces because that's one of the things that Anke is interested in.
Yes, very much. I was at least expecting one person on from these places who may be interested to that. So thank you so much for Anke for joining us. Otherwise, it's not worth it for me just to talk about this thing. What we are trying to talk here is that how quantals naturally appears in different areas of mathematics. And in some papers, I recently found that Z ideals and D ideals, which are two specific type of ideals, I forgot the definition of D, which appears in the context of these spaces. And these two people actually wrote 3 papers with this title of on Z ideals and D ideals on these spaces. And they literally studied the several notions and properties from the theory of rings of continuous functions. CX means the rings of real valued continuous functions. And that's the area where first Z ideals has been studied thoroughly in the book of Gilman and Jadison called Rings of Continuous Functions. By the way, we have 3 very specialists on rings of continuous functions in South Africa, namely Dharmanand, Babulal, Themba Dube, and Parthapratim Ghosh. All of them have extreme expertise on these rings of continuous functions. So the question is that what they are trying to do, that concentrating on this D-space structure and study the Z ideals there. Now, what is a Z ideal? If we take, I'm just giving the commutative definition, but similarly one can extend to the non-commutative version of it. So if we have a commutative ring, and if we take all the maximal ideals who contains an element as a set, then any ideal is called a Z ideal if it satisfies this property, what is written here. But of course, there are some equivalent definitions of the same one. So this could be another possibility. Now, these papers actually studied Z ideals. And as I just mentioned that Z ideals already been extended to Z elements. Very recently, the first paper is written only in 2019 for multiplicative lattices. And as I just said, Themba and I are currently working on the Z elements. The question is, first we need to see that how quantals appears in function analysis. And if I remember that when last time Bruce was giving a talk, after his talk, I asked him some questions. And of course, we first sit down and write it down everything in details. But it seems to me that in some of the these spaces could be examples of quantals. So, Anke, just to tell you that quantal is nothing but a complete lattice with an extra binary operation, which is associative, and it actually distributes over arbitrary join. I think you were there, right, Anke, when I was talking on the last time?
Sorry?
You were there, right? When Bruce was giving a talk and then...
Yes.
Yeah, okay. So the idea is that which Riesz spaces are quantals? If we can understand some natural examples of Riesz spaces are quantals, and then one can actually think to generalize or extend these Z ideas to...
Can I suggest to maybe hop to the first slide so that we can look at the definition of quantal one more time?
Sure.
While we're talking about this.
Yeah. Okay. So what is a quantal? So quantal is just a complete lattice with a binary operation such that the operation is associative. And of course, to connect these two structure, lattice and operation, then it's actually distribute on left and on the right side. And there could be some special type of quantals when multiplication is commutative, or it has a multiplicative identity, taking the top element of the lattice as the identity. And once it becomes commutative unital quantal, that is also known as multiplicative lattice. So there could be examples in Rie spaces which are just simply quantals, or there could be also examples of Rie spaces which are multiplicative lattices in this sense. So if we can see such natural examples in the context of functional analysis, then one can study more quantal theoretic properties of it, or one can study these Z ideals, D ideals type of things to the corresponding Z elements or D element kind of things. So that could be one way how functional analysis can be connected or related with this study of quantum. Then the very interesting paper, the last one I very recently found, it connects very deep, apparently three different areas, like some analogies between commutative rings, Rie spaces, and distributive lattices with smallest element. So this paper actually motivates me more for opportunities or possibilities to get the relations or connections between these three different research areas in some sense. So this could be another angle from which one can think that how one can get quantals in a natural setup of different structures which appears in functional analysis. Okay, now let's talk about category theory, and better not to speak anything about category theory because almost everything what I mentioned thus far actually can be viewed from various categorical aspects. And I gave a definition of a quantal at the very beginning, but quantal also can be seen as a monoid object in these closed symmetric monoidal categories of soup lattices. And category theory is one of the research area where quantals have been explored enormously. The other research area where it also very much appears is actually mathematical logic. Of course, I haven't studied these things, but I just found this interesting analogy that quantal gives us semantics for propositional linear logic, as Boolean algebra gives for the corresponding classical propositional logic. So category theory and mathematical logics are the two areas where quantals have been explored quite a lot, and they are quite also interrelated with each other in different papers. But the question is that how far we can further correlate these areas like topology, algebra, or specifically on the rings type of things, and generalize it, and then study the corresponding categorical properties of it, or also see some kind of the logics, how naturally appears on these results, which appears either in the context of topology or in the algebra. So these are the very, very few observations so far I have noticed, and then I thought maybe I share with you. And of course, your expertise in different areas can shed lights on this and can think that how we can think about this and see the possible correlations and establish some new ideas and then start the whole process. So with that, so let's start our discussions, what we can do. Thank you, Zurab. Thank you, everybody.
Marco. Maybe what we can do is like go around and each of us can either ask a question or say something they know about quantals, or maybe suggest an idea that they could have gotten while they were listening to your talk.
Sure.
Zurab, if I may just chip in here, there's something I just want to point out in Omoto's slides.
Yes, Themba?
Let me show my face.
Yeah.
Yeah, the second slide, Omoto, the way you had a blank on the ring side and you had something that looks like compactness on the quantal side.
Okay, let me share. Is it sharing? No.
Not yet.
No. Okay, now it will. This one, right?
No, I think one up. Yeah, this one, this table here. You see there where you've got a blank on the ring side. What actually should go in there is a finitely generated ideals. It turns out that now, if you're working in the quantile of ideals, the compact, because the thing what you have on the lattice side, that's exact
Yes.
compact. The corresponding thing on the left is finitely
it will be finitely generated ideals.
Yes. And if you are working in the quantile of radical ideals, then it will be the radicals of finitely generated
of course.
Yeah, exactly. The
okay. Sure. Okay, then. Thank you, Temba.
So let's go around the table, so to say. I can call out names if you'd like me to, according to who I see on my screen. I think I see Anke. Anke, would you like to say anything?
Sorry that I came too late due to this technical issue. When I saw the definition, I was wondering whether the set of components that Bruce was using in his talk, it seems that this has a very close connection to your object of a quantal, because you have the zero element, you have the one, you have a natural multiplication, which is just, so to say, the infimum of 2. And I would guess, I have to think through it, but I would guess that there is a connection to our theory of free spaces. But I have to check it first.
Yeah. But
the multiplication there is infimum, you said, right?
Sorry?
Multiplication there is is multiplication meeting in the context. So then this would be more than a quantile. This would be a frame.
Yeah, even more. Yeah. Okay.
Which is, of course, a very interesting object and very well studied in South Africa.
Okay.
Yeah, and I think Bruce did mention that also one should study that frame. Could you explain, because there are some colleagues here who were not there at that meeting, exactly how we get that frame out of a read space?
You take, so in Bruce's setting, you have a weak unit. So when you generate a band out of it, you get the whole space. You always can think of the L1 space on a probability space, and then you take the constant one, the almost everywhere constant one function, to the equivalence class of this. So as a weak unit. And what you do in the probability theory, you multiply by characteristic functions. Yeah, and these characteristic functions are practically the components of the constant one functions. Yeah, and this concept you can do abstractly by saying, okay, what is a component of a unit? It's an element between 0 and 1, such that the disjoint element has the same property. So the unit minus this element p, that is called p. P is a component if the unit minus p is disjoint to p. As it is for this
structure, are we now in a read space, or are we lattice or space? In which structure is this happening?
Sorry?
Abstractly. In which structure are we? Are we in a read space?
We are in a read space. We have either an order unit or a weak order unit.
And what is the definition of that kind of unit?
This is a more general concept. You can take any element and then look at components. But
for element where?
Huh? In a read space. So a component of an element is just an element in between 0 and this element, such that the element p and the upper element minus p, these are disjoint. And for us, is of interest the components of this unit. So, but this is a totally abstract concept that exists here.
Yes.
Yeah, So that's why you can take all components of your unit elements, and I think this has all the structures you have here in given of your whatever you call it, however you call it, frames or quantals or whatever.
So is it a complete lattice?
In Bruce's setting, yes, we start there with we started with a Dedekind complete lattice, because the classical L1 space over a probability space, it is Dedekind complete, meaning that any set that has an upper bound has a supremum. Yeah, the supremum exists for all of these bounded sets, and this is what we have. Mm-hmm.
And
so
does it by any chance?
Sorry?
Does it by any chance also have this multiplicative identity as a top element of the lattice, or it will be too much to ask?
No, I think. Can you show me your definition again? I think the unit is that what you call one?
Yeah, one is the top element of your lattice.
I think yes. Yeah.
So because we're taking components of the unit will be the biggest element.
Yes, of course. You have no. These
are
taking
an element and taking things below it.
Exactly. Okay. And the weak order unit, the constant one function is your one. Then you have the zero function, which is your zero in the L1 case, or abstractly in the Riesz space. And you have all these components in between. And since we have a Dedekind complete lattice, we have many of them.
Mm-hmm.
So this would be a very interesting construction to study. I think we did say last time that this construction is actually functorial. Maps between Riesz spaces preserve these kinds of things, right? Am I right? Am I correct, Anke? If I have a map between Riesz spaces, does it not preserve this concept of a component?
Only if it is a Riesz homomorphism.
Yeah, sure. That's what I mean.
Yeah.
Only then. Yeah.
So we will get we might get an interesting functor from the category of Riesz spaces to the category of frames.
Yes.
So that's one thing to look at for us going forward. That's great. Now let me see. I think Temba, you already said something, but would you like to add anything?
No, nothing. Just one thing that I heard last year from George Chanelidze, which I was not aware of, that the category of frames actually forms a reflective subcategory of that of quantiles. That does not seem to be commonly known, you know? Okay, thanks. There's nothing further, Zurab?
Yeah, that would be actually good to either find a reference for that or kind of write it up ourselves. That seems like a fundamental fact as well. Jeff, would you like to contribute with anything?
My way into quantiles has been through theoretical computer science, and where it was the semantic space of linear logic, as Amartya said, and that offered a semantic space which could prove consistencies of laws so that we could reason about laws. So actually, I use quantiles to get rid of them, to replace their structure by laws proved consistent with respect to them. So that's not very much help, I'm afraid. Maybe what I can do is ask something that I was curious about during the talk. The quantum mechanical aspect, which provoked the whole thing, seems to have been shoehorned into operator theory as part of the C-star algebra structure or something. Is that right, Amartya? Where did quantum mechanics go?
Honestly speaking, I haven't studied that part, but Mulvey's main idea was to get these non-commutative C-star algebras and study it from the locals point of view. And that's why how we actually developed it. And I have seen many papers written, because nowadays there is a branch of research called non-commutative geometry. As you know, where C-star algebras appears very naturally as one of the starting point to redo everything as algebraic geometry is doing, but in a non-commutative setup. And then quantals naturally appears in their studies. But honestly speaking, Jeff, I do not know anything about quantum mechanics. So, but I believe I'm sure that people based on the papers, what I've have seen on the internet that people are very much interested to see this Mulvey's approach to understand the foundation of quantum mechanics. But maybe an expert on quantum mechanics can tell better how far it is successful.
I
or how
should
far
sort
is the
that
current
out because
state
it will
of
be
research.
easy for me to sort it out. So I should do so.
Oh, thank
Okay,
you, Jeff.
that will be
Yeah, that
fantastic.
actually would be very, very interesting. I had no idea that quantals are related to, so that quant was actually related to the
Yes,
other
yes,
quant.
yes, yes, yes.
I had no
That
idea
was
about
his
that.
idea.
That's
That
very
was
fascinating connection. Yesterday there was a very, very interesting colloquium talk where the speaker spoke of open quantum systems. So basically, if a closed quantum system is some big Hilbert space, an open quantum system is when you decompose that Hilbert space into a tensor product of other Hilbert spaces, and then you look at kind of the energy exchange between so one of the components of the decomposition is an open system, and then he was interested in deriving a formula for energy leakage from the open system to the rest of the system. And the approach was kind of to see, because there is something called Schrodinger's equation that holds in the closed system, but in the open system doesn't hold. And the speaker was talking about that. And now I'm getting curious whether all of this has anything to do with quantals as well. But I want to come back also to Jeff about the semantics that this quantals give. So what is the logical interpretation of dot in that context, Jeff?
Dot. Well, we have, it's either sequential composition or parallel composition, depending on whether you're considering sequential or communicating systems. And the order is the this is going to sound a bit weird, the order of demonic non-determinism. By non-determinism, I don't mean probabilism. I mean, it's what's called demonic non-determinism. Like a proper relation is, which I mean, proper is not a function. A relation which is not a function is non-deterministic in that one starting state might be related to several final states. That's called demonic non-determinism. And the refinement of it means narrowing down the non-determinism. And so there's a supremum or minimum, depending which way around you do it, ordering that embraces that ordering. And that allows you to refine a specification to a program in theoretical computer science, where refinement means removal of non-determinism because an implementation is deterministic. Even if it uses probabilism, it's deterministic. Does that make sense?
Yes, it makes sense as much as I understand these things. I mean, and it also kind of reminds me again of yesterday's talk where the speaker was saying that because of the fact that the open system in a bigger closed system kind of cannot control what happens with the rest of the system too much, there is some kind of non-determinism is exactly the kind you said emerging there as well, where something stops being a function. And yet again, now I'm wondering even more whether that talk yesterday has anything to do with quantals.
Well, I think there's something funny going on there. I didn't quite get that. I noted exactly the point that you're talking about when he said it, but remember that quantum systems are reversible. No energy is lost. He made that point too. And so if it's reversible, how can it be non-deterministic as well? So I didn't quite get that point.
Right. Okay, that's interesting. We maybe ask him. He's still in Stellenbosch for the next couple of days.
Yeah, he seemed like a good guy. He visited Ames a year ago, and I noted him then as one of the guys that I thought we could work with. If I can express it so arrogantly. But you know what I mean, right? Some people just aren't.
Sure. No, I know what you mean. Vivian, you're next, at least on my screen. Would you like to contribute with anything?
So I was just I can't I'm not clear if you just said fractals, and did Jeff just say something on computer science? Yes. Did you say fractals, Zurab?
Fractals? No, we were talking about quantals.
Okay.
I don't think I said anything
because
about
now
fractals.
because of the non-commutativity of what the operations are, I now thought about iterative function systems that generates fractals. So I
Right.
think it can be applied in dynamical systems. To generate fractals, you usually apply those iterative. It's called IFF, IFS. Jeff, you can help me. Iterative function systems, I think. So the order, the sequence, the order of the operations applied to data, in this case in application, can the order can give different structure. So yeah, sorry, I just thought you said fractals and then Jeff computer science, so I just connected both of them. But at the same time, with the non-commutativity and what's the other one? Yeah, for the sequential time dependent, some data, they are time dependent. So I just was relating that to the sequential operation that happens when you do, when you generate data. So I think that I'm just applying it to dynamical systems terminologies that I know.
I had the same thought as you, Vivian, probably at the same point when Amartya mentioned the different topologies, Scott and Lawson and things like that. I was thinking, what about Hausdorff dimension? And the difference is that, as just you've emphasized, those systems are dynamical, and I'm not sure where that comes into this.
Well, there is like quantum topological dynamics, but I have no idea what what that is. Maybe that's the area. Yeah, but yeah. So I think
What did
I
you
know
say?
where
Quantum. Please repeat, Vivian.
quantum dynamic systems.
Quantum. Okay.
Maybe Amartya. Okay, I'm not.
Yeah. No.
Yeah. But just because of this ordering of of operations, where you can where the ordering a different order gives a different result, in this case the fractal generated.
So kind of trying to think about what Vivian is saying. I mean, in principle, you could have X, Y, and Z being endo functions over some space, right? Where dot is composition. And then you should be able to join your functions. So you could have a kind of dynamical system that looks like a quantal.
Yeah.
I'm just guessing wildly now, not really making much sense apart from this formal relationship between the ideas.
No, I was just yeah, is the only thing I can relate to what I know, to quantum.
Yeah, I mean, dynamical system we can think as a semigroup action. I mean, which
Yeah,
itself
definitely, yeah. Continuous
have a
dynamic
starting
system.
point towards the quantal, but only we need to just try to understand what just Zurab mentioned, that how to get this meaningful join thing as an event in the dynamical system, because the product is already there. That's not a problem. Just we take in time t1 from x to y, in time t2 from y to z, and this compose. So that part is fine. Maybe who knows?
That's the semigroup property.
Well, if your dynamical system acts on, I mean, if your transitions are already on a complete lattice, right? Then you can component-wise join the operators.
Yes. Yes. If your underlying structure is already a complete lattice, yes.
Yeah.
Yes.
All right, that's interesting. Maybe we will come back to these ideas. But so Jeff, would you be able to concretize it a bit more? Thing that you thought of?
Well, the ordering, non-deterministic ordering, all I can think of is phrases for you to Google, or I could recommend a textbook by Ralph Bach. But it's called the demonic choice of two operators. The demonic choice is the greatest lower bound, and the angelic choice is the least upper bound, or the other way around, I don't care. And the demonic choice I've tried to explain is the intersection of two relations, so it's more likely to be functional, well-defined for an input, a single output. It's narrowed down both of them. And the angelic choice is rather difficult to explain, but it's not an implementations, that is programs, sequential or concurrent, are not closed under angelic choice. Yeah. Also, another thing is that infinite demonic choices, lower bounds, lead to non-continuous operators, so unbounded ones. So it's all the theory of semantics of sequential or parallel programming this comes out of. It was work of a Dutch computer scientist and an English one. The Dutch one was called Edsger Dijkstra, and the English one was called Tony Hoare. If I can get away with dropping names.
Thanks, Jeff. As you were saying this, I also it struck me also that when you mentioned relations, it struck me that we could also take relations as an example.
Yes.
Let's say we take binary relations on a set.
Yeah.
They will form a quantile, because join will be just union of relations, and dot is composition. Composition
Yeah.
does preserve.
So that's
join
exactly
relations.
what I meant by the sequential model of computation. It's
Oh,
called the
fantastic.
model, but it's a rather weak model. It's not really strong enough. That's the model of Tony Hoare. The model of Edsger Dijkstra, you replace binary relations by predicate transformers. Is that a phrase that you've ever heard before?
No, not
Okay.
really. But
It takes
yeah.
a predicate on the state afterwards back to a predicate on the state before, the weakest one, for which if you start in that state, you terminate in a state satisfying the thing you started with, the post condition, the thing on the states afterwards. So it drags post conditions afterward, the computation, back to conditions beforehand. And that turns out to be strictly more expressive, the predicate transformer semantics, than the binary relations, which came as a bit of a surprise to me, a couple of decades ago.
Wow, that's fascinating.
There is more than one than just the binary relation semantics you mentioned, Zurab.
Right. So, Morten, you see, you picked a topic that's really so interconnected with so many things.
It's not I connected it; it's already been connected.
Yeah,
I'm bringing it.
No, that's what I'm saying. So you got lucky with that pick of quantile. So did you hear the relational case? So you didn't have that as an example, did you? Binary relations on a set. I think that could be good.
Well, he had semi-group.
Yeah, I have the semi-group as one of the most primitive example. But what Jeff is telling, that based on that little bit higher level, of course.
Yeah.
Yeah.
Okay, great. So next on my screen is Kishan. Would you like to contribute to anything, Kishan?
Just if maybe you could tell us about the connection to metric spaces. I think there was continuity, something there. You mentioned a paper.
Are you saying that I should show the name of the paper?
Yes, and maybe if you know what results are established in the paper.
I haven't studied that paper yet, but I remember they studied continuity as well as they have a distance, the notion of a distance with respect to these generalizations. But I can send you the paper even.
Okay, sure. Thank you.
Sure.
Thanks, Kishan. Indra-san, would you like to contribute with anything?
Thanks, Zurab. I think the most peculiar thing is the title of this paper. What was it called? I don't recall. There's not much I can say about this structure, but I was also wondering about realizability. That seems to be interesting. Furthermore, given my following in terms of looking at countable sets, is there a countable version of these things? Lastly, convergence seems to be very interesting. How does convergence, how would that fit into this entire seems something maybe silly to ask. I really don't know the area, but it's something to think.
Thanks, Indra-san. Could you hear that, Hamoto? I was a bit struggling
Yes,
with
yes, yes.
connection.
No, definitely, that is really something one should study and explore. What this convergence part, because that's one of the crucial thing for which we actually do this generalizations of net and filters. We can't do it in a standard way. So it will be nice and interesting to see how convergence notions will appear there. Yeah, thanks for your feedback, Anderson.
Okay, so Andrew, I'm sorry, you're last but not least, definitely. Somehow, despite of the fact that both of your first and last name begin with a letter at the beginning of the alphabet, you appear on the screen at the end on my Zoom, at least.
Yeah, thanks. Thanks for the talk, Hamoto. My one question was, I didn't see it, but maybe I wasn't paying attention, whether the distributivity of the lattice is ever important.
Yes. For example, to prove that xy is less than equal to x meet y, somewhere we need that distributive property. But of course, we do not need infinite distributive property to prove it. Only finiteness is sufficient.
Okay. And yeah, I mean, the main comment from my side is this is very closely linked to stuff I've been working on for the last 2 years with Claudette Robinson, to do with residuated lattices. So there you would always have a monoid structure with the multiplication. So we would want it to be unital. In general, commutativity is not required, but and in the residuated lattice case, you always have these for the multiplication, you have these two residuals, which are usually indicated with a backslash and a forward slash, or maybe a left and a right implication operation. And then once you've got those, and you specify you can specify some element of the quantile, you can get negation-like operations as well. So with lots, the applications there are all to substructural logics. Yeah, so I sort of, maybe the question then is whether you've seen stuff talking about quantiles with additional operations that are derived from the multiplication.
I'm sure there are some special type of quantiles where they actually tweak these multiplication operations.
No, not special type. So every quantile would have those residuals, because since the multiplication on left and on right preserves joins by Galois connection theory, then you have an adjoint. So every quantile is of the kind that Andrew has been studying, but now Andrew is studying slightly more general, where you don't have necessarily arbitrary joints in your first set. So basically, quantiles without requiring, it's kind of literally dropping the infinite join requirement in quantiles, but still kind of keeping distributivity as far as we can stretch it in terms of what joins exist.
Yeah, so I was just interested if you see these additional binary operations in quantile, when people are talking about quantiles, do they talk about the residuals, or do those not really come up very often?
No, they also actually studied this residuated lattice, what you just mentioned. In fact, Dilworth has a number of papers on the residuated lattice. So they actually considered what you were saying.
What is that structure called, Andrew, the one that you're studying that's slightly more general than quantile?
So, I mean, ours is so I guess for us, we have residuated lattices, and then they've got this extra structure which turns them into what are called quasi-relation algebras. So this connects a little bit to what things Jeff was saying, where you're treating the multiplication like composition of binary relations. And the relation algebra stuff goes back to Tarski, but there you're requiring that the lattice is a Boolean algebra, which we are moving away from now. So we're looking at more general things where the lattice is at most distributive, but certainly not Boolean.
So I have a specific question. So we've got a lattice which has dot that's associative, and for which multiplying left by dot or using dot for left multiplication or right, both of them have adjoints. Is there a name for such a thing?
No, not unless you have the unit of multiplication.
But you do here. Sorry, I forgot about that. We do have unit here, so I should have included that.
Yeah. So then, if you've got left and right adjoints, then it would be a residuated lattice.
Okay.
Yeah.
Right.
And so that's stuff.
Lattices are slightly more general and quantile than right? Umberto, do you agree with that?
Yeah. Not quite general, right? Because it has some portion of the quantals, but it also added something and is missing something.
No, it's not. Quantal has everything that the other one has.
Unital quantals.
Unital quantal. Okay. Yes. Unital quantal.
Oh, sorry, I didn't get this. Okay, so quantal doesn't have necessarily identity element for dots.
One. Yes.
Okay, sorry, I didn't get that. Sorry.
Yeah.
Yeah. So very interesting. Thank you. Lots of links here.
Yeah, Andrew, the things you mentioned make complete sense to me. In theoretical computer science, the residuations are called weakest pre-specification and strongest post-specification, and they're used, every day in order to do calculations. It's exactly the way you described it.
Thanks. Yeah, definitely. The computer scientists seem to, there are many strong overlaps. But I guess, and one of the things that I don't know about is the relation algebra people are very interested in concrete representations of relation algebras or quasi-relation algebras, and I don't know about concrete representations of quantals as sets where the multiplication would be some kind of composition. I'm sure there must be people working on that, and I'm sure it's quite interesting.
Yeah, it's really fascinating how this topic brings several things together. Sorry, Jeff, you were saying something.
No, I was just going to add to that, that maybe the way to get, I don't actually know about these concrete representations, but maybe a way to get it is via Tarski representation theorem. That works in a very special case of a nice countably limited order, but maybe that general ultrafilter technique can be used in general to find these things, but I don't know.
Umberto, in your search of literature, have you ever found a book that kind of discusses all these different aspects and applications of quantals?
Not in one book, but there are some survey papers which includes algebra and category and little bit of logic aspects.
Right. So
it's a very long paper, and yeah.
Yeah, sure. We can continue.
Yeah, the other one is that there is a paper of Mulvey with Nawaz written 90s, which is a very long paper, 75 pages paper, where he discussed many aspects of quantals from the C-star algebra as well as category. So maybe Mulve's paper will be an answer to your questions to best of my knowledge.
I mean, we have lots of books in mathematics which are centered in a specific discipline, but then in every discipline of mathematics, various different mathematical structures arise. I don't think we have that many books that are centered on mathematical structures and that try to integrate the disciplines around those structures.
Yes.
Would you agree with that assessment, Jeff?
I would, though there has been a fight to gain it. The whole area, it's called Unified Theories of Programming. I think it's based on Galois connections between theories at different levels. So in my area, I'm interested in the way these various theories relate to each other, like skins of an onion, and each one up the filtration, up the hierarchy, adds more detail until you get down to something that's entirely deterministic. And this area has been explored by unifying theories of programming. It's an abstract setting for adjunctions.
Oh, wow, that's interesting. That's very interesting. By the way, one of the earlier discussions we had with the functional analysis group, we realized that there are quite a number of concepts that are very standard in one group, but completely unknown to another. Galois connections is actually seems to be one of such concepts. It seems like while some of us know these objects very well, it seems like a lot of mathematicians in other in areas that are a bit different to computer science type of abstract algebra type of mathematics do not know about Galois connections. So I think it would be good to have at some point a discussion about Galois connections on their own, and maybe Jeff would also help us with the applications to computer science.
Oh, absolutely. It would be easy for me to do that because I have hundreds of pages of notes that my graduate students have to read about the applications of Galois connections to computing science.
Wow.
Oh, fantastic. Okay, so can we ask you to give a talk for us on that topic?
Yeah, I'd be happy to think about that. Let me think about it for a couple of days and discuss it with you. Is that okay?
Of course,
Zurab?
yeah. Absolutely, that's perfect. In fact, in April, now we are going to have a mini school on read spaces, and it's going to be a very, very introductory course. So the idea is for us to get to know about some basic theory of lattice-ordered vector spaces. Anke, would you like to say a few more words? I think you're also involved in that, right?
Okay. So may I ask, so Bruce will start with this course, or what did you plan with him? I have not planned something. I have not planned with him so far.
Well, I just saw the announcement that Bruce was preparing together with the. Okay, so maybe we should ask Bruce then. I don't know anything more than you do, I think.
Yeah, we just had a rough discussion about this, that I could give these basic introductory things on ordered spaces, on Reed spaces, and operators on them, and all this, such that it fits to his theory in a good way. But he did not send me any plan, which dates we have and what exactly to do. So this has to be discussed.
Okay.
So how many sessions does he? How many sessions does he have?
So an ETAX mini school is usually a month-long thing. There is one session every week.
Of 1 hour.
I think it's 1 hour or a bit more.
Okay, good.
Yeah.
Okay, so I have to discuss with him how we arranged.
Yeah, that would be great.
And it starts when? Beginning of April or when?
Yeah, it's supposed to start in the first week of April.
Okay. Which is very soon. And do you have a certain date when it will happen?
I think the announcement is busy being prepared, but let me actually peek into the draft version of the announcement that I received today. according to this, the first one is going to be Tuesday on the 9th of April from 2 to 3.
Tuesday, the 9th of April, 2 to 3. Okay.
So I'm actually going to schedule in the chat.
So that is our, yeah, we are have an hour difference. Okay. Okay.
And another thing that we could maybe, so in terms of the future interactions in the research program, I think it will be quite useful if we start drawing up postdoctoral fellow calls for things that we're interested in. For example, Cyrene and myself, we after this, we will have a discussion about a possible postdoctoral fellowship that's linked with the mathematical structures and modeling research program. And each of us at our universities have opportunity of getting a postdoctoral fellowship for a postdoc. And I don't think we use it a lot. I mean, I for example, haven't had too many postdoctoral fellows. Actually, only once. The other time I had a grant, but then the person didn't write. So it will be nice to intensively have postdoc fellows, and then they could help us to kind of do the interaction between us as well, because we can come up with questions and the postdoctoral fellow can answer them.
Yes.
Bruce also likes that idea.
Joined us.
Bruce Watson also likes that idea. I don't know, how does it work at Ames, Jeff? Does Ames have any postdoctoral fellowships that they award?
Things have transformed at Ames completely in the last 18 months. I think the only postdocs that we have now are to do with machine learning.
Okay.
I don't know that anything else is available, but last week in Seacoola, David Holgate announced a special group within the research center at Ames involving topology and algebra, involving him and Karen Therese Hull. And so maybe they have something in mind, but I've not heard at all about that. I know that David Holgate will be coming to Ames on Thursday, and I'm booked him already for discussions. Otherwise, we're really short of money in pure mathematics at the moment. It's all being channeled to machine learning.
Okay, well, I think that the universities themselves have opportunities for postdoctoral. I don't think we will struggle to get 3 or 4 postdocs in our research program at least. But we somehow never thought of this before. So let's just do it. And some of them could be indeed collaborative. Others, maybe some of us wants to have their own postdoc fellow where they will work on topics they're interested in, which is not necessarily linked with our program. But if you don't have a postdoctoral fellow and university can grant you one, then I suggest that we try to collaborate on having a joint kind of a joint postdoctoral fellow that will interact with some of us in the research program. This will also strengthen, I think, our research program and the value that it plays in the context of NEPEX. Thank you very much, Amorto, for hosting us on this wonderful topic. So the next plan is that while you're gathering, maybe some of us who wants to work with you or among each other on Quantals, we will have the mini school on these spaces, slightly more general spaces in April. And then after that, we can come back to thinking what we want to do. But in the meantime, Jeff and I will talk about possible webinar that Jeff could give about Galois connections. Thank you, Andrew, for coming. I think we're going to stop here anyway, all of us.
Thank you, Zoe.
Yeah, just to add
so nicely, and Amorto, thank you for a really stimulating presentation. Wonderful work.
Thank you. Thank you very much.
Did you say, Amorta, you wanted to add something?
Yes, I mean, just wanted to say that not everybody need to be involved in every project within the Quantals. I mean, it's just a discussion. So just to start something, and then grouping will naturally happen between people. So not any kind of obligations that everybody have to be interested in every aspects of mathematics, which is very unnatural to expect. Yeah, that's what.
Sure. I think today's discussion, just like last time, I think it was a very useful discussion of knowing about things and finding out about things. It's something to have in mind.
Sure. Okay.
Great.
Thank you. Thank you, Zura.
Thank you,
everybody.
for joining from Germany.